Welcome everybody to this week's Ask an Astronomer live stream. My name is Stefan. With me I have Eric, and we are both PhD students at the University of Cambridge at the Institute of Astronomy. And we're here to answer all your questions about science, the universe and everything. And maybe we start by Eric, you saying a bit about who you are and what you do, what's kind of your area.
Yeah, thank you, Stefan. As Stefan said, my name is Eric. I'm a PhD student at the Institute of Astronomy in Cambridge. And also, like Stefan, I'm a cosmologist. So my area of study is the early universe, specifically the cosmic microwave background radiation, which was emitted, say, a few 100,000 years after the Big Bang, and that we can use to learn a lot about the overall structure of the universe and composition of the universe and its history as well. So that's what I do.
Cool. And for all people that are new, let me quickly explain how this works. So we'll just be online for about an hour here, and you can send us your questions in the YouTube chat, or if you're watching from Twitter on Periscope, you can send us questions in the chat. Or if you don't have an account on either of those platforms, you can go to Slido, so sli.do, and enter the code #astronomy. And then you get to a page where you can kind of, without an account, send us questions that will be shown at the bottom right there. And we'll try our best to answer the questions. We don't know everything, but we'll try. Okay, so we just got one question from YouTube already, so let's just start with that one. Do cosmic rays affect us? So maybe should I explain this, or do you want to, Eric?
You can take it, and then I have a tiny thing to add at the end.
Oh, okay. So cosmic rays are basically high energy particles that come kind of to Earth, to us, from kind of far away from space. So many of them can actually come from kind of different galaxies even. So they can come from very far away. And they are usually either photons, which we call gamma radiation. It's basically similar to, well, actually, most cosmic rays are similar to kind of radioactive radiation. It's just highly energetic particles that are flying towards us. And they're different kinds of particles. So it can be protons, it can be photons, etc. And what they do usually is they hit somewhere in the atmosphere. They hit kind of an atmosphere particle and produce kind of a shower of many particles that comes down on Earth. So usually the high energetic particles don't even reach us. And how they affect us, so I'm not sure. So on humans they have basically a negligible effect. Like the few cosmic rays that hit our body can kind of affect basically a single kind of cell or molecule, but this usually doesn't have a big effect at all. And in theory they can also have an effect on, say, electronics. So if like a cosmic ray would hit, say, your memory in the computer, it could kind of flip a bit or something. But I'm also not aware of that being a major effect, at least as long as you're on Earth. But Eric is looking as if he wants to say something about this.
So it is I mean, maybe not major, but significant effect if you just happen to be an astronomer. Imagine that. And then you quite often will get cosmic ray hits on your camera that you're using to take photos of, the stars.
Oh.
So did you not know that? Yeah. So that's something that needs to be taken out. And I believe it's also an issue for the computers that we have in space, like in the space station.
Oh, yeah.
So they have to be designed to be robust to problems that can be caused by cosmic rays changing what's going on in your computer memory.
So in space there are lots more cosmic rays hitting our equipment, because on Earth there's a magnetic field, and that deflects cosmic rays, mostly kind of to the poles, I think. Or in general, if you're on Earth, you are getting hit by far less cosmic rays than in space. Therefore, on the International Space Stations or on all spacecrafts, you have to use special hardware or shielding to stop your computers from kind of going crazy.
If I can say one more thing about it, I don't know all the history of science around this, but the way we heard it in undergrad physics anyway is that cosmic rays are a good way of seeing the effects of relativity in action, because if you get a relativistic muon coming in, which is like a heavy electron, it's just a particle, then it will live for much longer than a slower one. and that's because it has high energy. It's moving quickly, so you can see relativity in real time, kind of.
Okay, that's nice. I just noticed there's another question on YouTube. What is the pattern or algorithm of Big Bang which created life on Earth? So that we can search life in the universe for sure. Oh well, that's I guess the $1 million question maybe. I mean, the idea is not simple, but you can kind of put it into many steps. The problem is just we don't know what many of those steps are. So maybe let me kind of rephrase the question a bit and go from the beginning. So the question is, we have the Big Bang that creates lots of matter, and how do we arrive at humans living on Earth? Or actually, Eric, do you want to say something before I start answering this?
Go off.
Okay, my question. So basically, after the Big Bang, the universe is just full of gas without, gas doesn't think, gas doesn't feel, it doesn't make civilizations. And what you need to happen is basically you need to have kind of form a star and planets around it, so you have somewhere to build your civilization on. And then you have a planet that's kind of full of rocks and gas, and then you have to form life. So basically you have normal, what we call, abiotic or non-organic kind of molecules that you have to
abiotic,
form together into amino acids, cells, all this kind of stuff that life is made out of. And that, I think that some theories how this can happen kind of at random in kind of certain conditions, but it's all kind of very uncertain how this works. And then after you create life, you have to create kind of intelligent life. So you start with simple life, then multicellular life, then kind of intelligent life, then it has to create a civilization to get to our point. And what we think, or we're not sure if it must be, but what we think is very likely is that we need water to form life, because many of the processes that make our bodies work kind of rely on many of the special properties of water. So if we want to search for life, we usually search for water. And of course, also a step before that, we search for planets, because life without planets is kind of hard. So the two main points that we use today is, search for planets around other stars, so-called exoplanets, and then maybe search for life on those planets. Or search for life on planets in our solar system. You might have heard the excitement about Venus recently. And also, I just see the question on Slido that asked for one of the planetary guys from the IOA. I will go and ask the planetary guys to come on our live stream, and maybe we'll get the planetary guy next week or in one of the next streams.
Sorry, I couldn't help you this week.
This week you have to deal with two cosmologists. Okay, we got a few questions on Reddit as well, so I'll go through a few of them before we go back to the YouTube question that I just saw coming in. Why didn't the universe collapse into a black hole right at the Big Bang? That's I think, really nice question. Should I answer it?
Yeah.
Sorry,
I know you already have an answer prepared, so I'm giving it to you.
Yeah, actually, we got this question a few weeks once before, so I thought I'll start with this one. So basically, the idea of a black hole is when you have a kind of a clump of matter in a vacuum that is compressed small enough, then it can form a black hole. So the mathematical kind of expression for this is the so-called Schwarzschild radius, and depending on the mass, everything has a certain Schwarzschild radius. And if this mass is compressed into an area or into volume smaller than its Schwarzschild radius or volume, then you can form a black hole. Then this forms a black hole, because in simple terms, kind of gravity is too strong at the edges to kind of let light out and gives you all the black hole effects. But this only works if everything else around it is a vacuum. You can imagine if you have not kind of a clump of matter isolated in the vacuum, but just matter everywhere, then the gravitational pull from the surrounding matter will cancel out with the gravitational pull from whatever matter you would consider the black hole. So you can't, then the kind of Schwarzschild radius idea doesn't simply hold, and it's much more complicated to calculate what is a black hole. So basically you need something that's more dense than the average, and that was not necessarily the case in the Big Bang. So our current models of what we call inflation usually say that the density fluctuations were not that large that you would form black holes. So they were slightly more dense at some places than others, but the difference was not large enough to create an actual black hole. although there are theories that this could have happened. That's what we call primordial black holes, but we haven't found them yet, let's say, and we're not sure if they exist.
Basically, you shouldn't imagine that at the Big Bang you had a really tiny super dense point and there was a bunch of space around it that it went into. Like that would be the vacuum that Stefan was just saying doesn't exist, right? You should think the whole universe was contained in a tiny dense point that expanded. This gets to where our intuition fails. But
Yeah, okay. Another part of the question was, what is the curvature of the universe? Is that what you want to explain?
There is no curvature; it's flat, don't you know?
I'm not
Sorry,
that sure about this.
Cosmologists joke. So, what's the easiest way to explain curvature? So, in normal Euclidean geometry, like you learn in school, that is what we call flat space. So that's everyday normal geometry that we're used to. For example, one of the best known things is that angles on a triangle add up to 180 degrees. You can have other geometries. So if you think about, say, the surface of a sphere, like the Earth, then if you're living, like we happen to do, on the surface of the Earth, then on large scales, you get new rules of geometry, say. So if you make a big triangle that goes from the North Pole to the equator and then over a bit and then up again, then that triangle is going to have, they are all at 90-degree angles, right? Yeah, they can be. Maybe. Anyway.
Yes, so the two angles at the equator will be 90 degrees plus something at the North Pole, so definitely
Exactly.
more than 180.
Thank you. So basically the point is you can have this kind of thing in a larger scale as well, where the whole universe could have some non-flat geometry on a large scale. And this would affect how it evolves over time. And if it was what we call closed, like a sphere, then in principle, if you go in one direction long enough, you could come back the other way, and things like that. There's a bit of a debate these days of whether or not it is flat. That would be regular geometry, basically. And people thought for a little while that it was, but now there are some questions being raised. We don't need to get into that, though.
I mean, even if it is curved, we know that's very slightly curved, so you won't notice it in everyday life or kind of anytime soon. But we are not sure if the universe is completely flat or slightly kind of curved. Okay. The deformation of space-time caused by a planet, can it be measured? Is a question.
Absolutely.
Go ahead. Do you want to explain? Do you want to give an example of when we measured it?
I mean, sure. When you're hanging out on Earth, enjoying this nice gravitational fields, you're measuring the deformation of space-time being caused by the planet.
Well, okay, that's the thing. Yeah, I mean, you can basically take a pen, let it drop, and you can argue that this is space-time because general relativity. But also, I think there are way more direct ways of measuring it. Like basically, you can take it.
That's the most direct.
Okay,
to expand on my slightly flippant answer, which I apologize for, in the context of general relativity, which is our best theory of gravity that we have at the moment, you can view gravity not as some force field like one would in a Newtonian picture, but instead as things deforming space-time. So then, in that sense, the Earth is making some dent in space-time, and that is what we would perceive as gravity. Do you want to carry on with what you were saying? I just want to.
Yeah. My favorite experiment is basically take two atomic clocks, put one on Earth, bring one into space, wait a few months, bring them back together, and notice that the time is different. So that's basically also an effect of the deformation of space-time. That the gravitational field of Earth kind of slows time. Another one is what we did with some spacecraft. I think I'm not sure which one it was. I think one of them basically when a spacecraft we send and it goes beyond Jupiter or beyond some planets, I think we can measure the time delay from the signal from us to the spacecraft, and I think we can measure the effect of the planets. It's called, I think, Shapiro time delay, and I'm pretty sure it's measured in the solar system. So that's actually really impressive.
You also often hear the example that that GPS satellites need to be very precisely timed, so you have to account for relativistic effects there.
Yeah. So actually, almost an everyday life thing, the dilation of time and space on Earth. We got a few questions about kind of the beginning of the universe. So we got one, how does the universe come into a point? And another one on YouTube, what is making the universe expand? And where is it expanding into, I guess, or why is it expanding? So to answer the first question, we don't know how the universe kind of began, like how it was created, you could say. We know basically what happened after the first, fraction of a second, but we can't really know how everything began. One thing I want to know, though, is the universe wasn't a point at the beginning, or at least as far as we can tell. We just know it was really, really dense, and maybe, yeah, very, very dense. But basically, kind of the universe got expanded. But today, it's, at least observable universe is like a few billion light years large. But then at the beginning, it was really, really tiny, but it was not necessarily like a point. It was kind of at least, like it could have been infinitely large at the beginning. We don't know. We can't see further than a certain distance. But it wasn't a point. But although that's often kind of not so nicely represented by the plot that I show you here in the slide. What is making the universe expand? Basically, well, I mean, of course, we don't know where kind of all the stuff that the universe comes from that is there now. But we see there's a certain amount of kind of energy in the universe, a certain amount of matter, and various other kind of things in the universe. And basically, you can imagine this like kind of imagine an explosion where you have lots of particles flying away from each other. And the reason they're flying away from each other is they have lots of energy. And in particular, they have more energy than kind of gravitational attraction or other attraction that they have. So basically all the matter in the universe, especially in the early universe, has a lot of kinetic energy, so it's kind of moving fast, and that's why it's expanding. And this kinetic energy, so that movement, is slowed down by the gravity of the universe, so it's kind of, this gravitation slows the expansion down, which is why in the early universe we see the universe expands fast, very fast, and then slowly kind of the expansion slows down. Of course, recently everything got mixed up again because there is dark energy in the universe, which made it accelerate expansion again a few billion years ago. But at least for the early universe, the basic idea is there's lots of energy, which makes particles move away from each other, which makes the universe expand. I'm not sure if that was a perfect explanation, but it's kind of the way you can imagine it. Okay, I see you got a few planet questions. I'm not an expert on planets at all, but I think we can try. Do you know something about how...
We can give it a shot.
How do astronomers determine atmospheres of exoplanets?
So my guess is that it's with spectra from transits. Does that sound right to you? And if so, I can explain what that means.
Yeah, I think that's what I heard in talks that exoplanet people have given at our institute.
Okay, right. So a transit is when you see, it's these days one of the biggest methods of detecting exoplanets, largely due to the Kepler mission, which detects a lot of exoplanets. That was the satellite telescope. And a transit is just when you have a planet, or it could be multiple planets in the same system, that go, from our perspective, in front of their own star. So that will make, if you're observing the star's light, that'll make a dimming in the intensity of the light from that star as the planet moves across, and also a smaller dimming when it goes behind, when the star obscures the light from the planet. But anyway, That's why in certain situations, maybe. We're not experts, is the caveat to all this explanation. So if you look at the spectrum of light that comes from the star, which is you don't have any spectra here, do you?
I don't think I have. I can check, but I don't.
That's unfortunate. Okay, so that's just splitting the light into all of its colors, right? Into the different components. Um, eh, Not super helpful, but anyway. So you can see usually in a spectrum different spectral lines. So that can be absorption or emission features, different uh, then of different molecules, different substances that might be present. So fundamentally, if you see certain features during the transit, then that you can associate with particular molecules, then you would be able to say, oh yeah, these should be in the atmosphere.
So yeah, right, to your question on YouTube, we do observe kind of the absorption spectrum. So you watch, the planets, the sun's light, the star's light, more or less well. I mean, you can measure it. And then the planet goes in front and you see, oh, oxygen absorption, like the frequency corresponding to oxygen is missing. Maybe there's oxygen on this planet. It's not usually oxygen. I think they're like, there's a few lines that are easy to measure and others that are hard to measure. So there are certain lines that people are looking for, possibly certain lines that indicate life. But I'm not an expert on which lines exactly those are either.
So I believe this was meant to be done with James Webb Space Telescope, which, for those who may not know, is a new space telescope that will be launched eventually.
Next year, I heard.
Is it now scheduled for next year? Great.
I think so.
I hope it does.
We got a question if there's any.
I don't know if it's been done before so much.
Sorry?
Anyway.
Oh, okay. Anyway.
I was just saying. Yeah. Go ahead.
I'm not aware of a planet around Vega, but I'm not sure. I never heard of Vega, like Vega B or something. So yeah, probably not. Can a planet merge into another, maybe by their orbits meeting or some kind of moon-Earth crash situation? Is a question we got on Slido. So basically, I don't think planets merge really after they form planets, but in the stage where planets are forming, there's a lot of merging going on, or at least like kind of crashes and accretion. So basically, when a solar system forms, there will be a star kind of at the center, and it will form a disk around itself with all the kind of material that's left over that's not in the star. And this material will eventually form planets. And what happens is, if there's kind of enough material at one point, it will accrete into a big clump of matter, and this clump will kind of, more of the matter that's surrounding it will fall onto this clump. And basically this clump will go around the star and collect all the matter that's on the ray. So when you look at a very young star, you see like this disk around it where the planets are forming, and you see gaps in those disks. And those gaps are basically planets that are going around and cleaning up their orbit, is what we say. So basically they kind of, yeah, right, there's also a YouTube comment mentioning this. So then they kind of collect all the material. No, planets do merge after they form when the disk dissipates. There's proof that information tells it. Okay, so there we just got a comment from YouTube explaining this for Uranus, that there was apparently a merging event happening after it formed, which kind of impacted its rotation. But yeah, usually planets only merge kind of in the early time, because afterwards, like one of the definitions of a planet is what we say, it has to have cleared its orbit, so it has to have cleaned up its orbit already. Otherwise, it's not a planet. So usually these mergers don't happen after something becomes a planet, because there's nothing to merge anymore with. Okay, so thank you for this question. Let's get the next one of those questions that we got from Reddit. We got two questions about Hawking radiation. One is what happens to the matter that fell into a black hole after it evaporates due to Hawking radiation? And the other one is, has Hawking radiation been observed and proven experimentally? And for that matter, is it even possible to measure Hawking radiation experimentally? Do you want to explain what Hawking radiation is, or should I do that?
I can give it a.
Oh, I think your internet connection is a bit unstable. Do you hear me lagging as well?
What was that?
I think your internet connection is a bit
No,
unstable.
you sound okay. Probably.
Okay, it's good now. Let's try again.
Not much I can do about that. So Hawking radiation is basically a quantum effect that was calculated out by Stephen Hawking, of course, in which black holes radiate according to their size. And yeah, that's pretty much it. You'll often hear a thing about some story about particle antiparticles or something. I read a little while ago that is not a good explanation of Hawking radiation. But I can't give a good alternative. I'm sorry.
Okay, so yeah, I guess then to the questions. Did we ever have observations of Hawking radiation? I don't think so. I'm pretty sure. No, I know we didn't.
I don't think so.
But is it experimentally possible? So as far as I know, it's very hard because basically it's kind of a very weak effect. So you would have to get very close to a black hole to measure it. But I guess sadly or luckily, there's no black hole close to Earth. So we'd have to get to a black hole first. Or I don't think we can measure it from Earth in any meaningful way, like even with very futuristic telescopes.
Yeah, I think it'd be extremely tough.
So basically look
right,
for
because the ones we measure would usually be. Do they ever measure stellar mass black holes?
I mean, I think, yeah, for example, in kind of X-ray binaries. So in binary systems, it's often easy to measure black holes or to find black holes because they accrete the material of the second star and then they shine in bright colors of X-ray. But of course, that's not Hawking radiation. I'm not sure if we know of like small black holes. And I know we know of large black holes, and I'm not aware of if we can actually observe small ones that are not happen to be kind of in a binary and accreting matter. But yeah, basically what we have to do is go somewhere where there was a supernova recently. Well, not really recently, but somewhere where the black hole in the galaxy, probably send a probe there and measure the Hawking radiation. So I imagine that's very difficult and very, very futuristic for now because we can't even reach the nearest star to us. Yeah. We got a question on Periscope. Have you worked with SDSS? Oh, sorry, I forgot to answer the second question as I posed. What happens to the matter that falls into the black hole after the black hole evaporates? So you just explained this kind of Hawking radiation thing that black holes send out radiation and basically they lose energy. And we say black holes evaporate. And basically stuff falls into the black hole. Say you take a letter that you write some secret information on, throw it in the black hole, and then a few billion years later the black hole is evaporated and all the radiation that comes out of a black hole is just random noise. So a common question to ask is kind of where did the information go? Because usually, well, yeah, I think information shouldn't get lost like in theory. But yeah, that's a bit of I think it's actually an active research topic, like what does happen to the information. And do you know more about this?
There was some article about this recently. Apparently there's been progress, but I didn't read it, so.
Okay, next time we'll have a
Look
black
up
hole
the
expert.
black hole information paradox if you're interested.
Okay, next time we have someone who knows more about this, we'll ask them all the black hole questions. For now, let's go back to the Periscope chat. We got a question if we have ever worked with SDSS observations. And SDSS refers to the Sloan Digital Sky Survey, which is a very big and well-known kind of galaxy survey. Well, I haven't really worked with the data in any kind of direct way. As probably most cosmologists, I have to use their likelihood to. So basically, the SDSS collaboration makes lots of observation, does a lot of work analyzing these, and at the end, for kind of most cosmologists, what they're interested in is A, the measurements they make of kind of cosmological parameters, and B, their a code they give us. So basically what we call this is a likelihood code. And what we do as cosmologists, at least what I did once in a while, is look if some model of the universe is a realistic model. So what we do is kind of simulate this model and see what observations we would get, and then compare these two, these predictions to actual observations. And for this, we would use the code from the SDSS collaboration and see if it agrees with the observations. So that's kind of the way I used the data, but it's not a very direct way. It's basically just take their code that they have produced, plug in my results, and see how well it matches. Okay. We got a few. Yeah.
BOSS is from SDSS, right?
Yes. BOSS stands for baryonic oscillations. Okay, I'm not sure exactly what it stands for.
I don't know either.
Maybe
I have it here, Baryon Oscillation Spectroscopic Survey.
Okay, and it's a part of the SDSS survey, so it's kind of a type of analysis they do, I think. Which is the cosmologically most interesting part. Well, not necessarily most interesting, but very interesting part is this analysis of those baryonic oscillations, which is the kind of BOSS part, which is often used in cosmology. Okay. Back to the YouTube chat, I would say. We got a nice discussion going on there about the planet merging thing. And we got a few questions. How do we know which element absorbs spectral light? So earlier we were discussing about kind of, you see an exoplanet and you want to know, oh, there's a gap in the spectrum and we know this gap corresponds to, say, oxygen. But how do we know this? This actually is not that hard to find out because we have oxygen on Earth. And what you can do is, just take a box of gas, take a light source at the one end and a spectroscope at the other end, shine the light through and see what is missing. It's not that easy as I'm making it sound, but basically we can measure this in the lab for most kind of materials and measure what frequencies they absorb. And then there are like big databases, big tables where you can just look this up. Where are quasars formed? Do you know, Eric, like details? I mean, basically everywhere where you have a supermassive black hole, you get a, well, not all supermassive black holes are quasars, but all quasars are supermassive black holes. So to get a quasar, oh, maybe I should explain what a quasar is, I forgot. Do I have a picture? I mean, not a picture, but an artist's impression of a quasar. Here, there we go. I think it's good enough. So what happens when you have a big black hole somewhere, say, in the center of a galaxy, is that material from the galaxy falls into the black hole. And all this material loses energy because, when it's far away from the black hole, it has gravitational energy, and when it falls in, it heats up, it has lots of kinetic energy, and all gets converted to various forms of energy. Basically, imagine a meteor falling down on Earth. It also emits lots of energy. Now you imagine this lots of times stronger with lots and lots of more meteors, and you basically got what we call an accretion disk of a black hole. And these disks, emit a lot of light and other radiation, and because they're so small, if you look through a simple telescope, they might look like stars to the eye or to the observer in general, which is why we call them quasars, quasi-stars. So the difference to stars is they're really, really far away, so they're much, 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 much brighter than stars. Actually, a single quasar can be brighter than the whole galaxy it's living in. But not every galaxy has a quasar. So luckily, the Milky Way, its black hole is not active, that's what we say. So it's not a quasar. It's kind of not shining brightly. But some other galaxies have, and I can't name one now, but plenty of galaxies have quasars. And how we detect them is basically look into the sky and look for bright objects. I'm not exactly sure how we distinguish between kind of a galaxy as a general and a quasar, but I think either the brightness or at least the spectrum of those are very different. So the spectrum of a galaxy is just kind of starlight mostly, while the spectrum of a quasar is very highly energetic radiation. So it's usually X-ray radiation.
So, I mean, they're called quasi-stellar, so they're going to look like a star basically, but high redshift.
Yeah.
I think. I've only looked at high redshift quasars, so if there are lower redshift ones, I don't know anything about them.
Oh, here's a good question on YouTube about those spectral observations of exoplanets. if they are possible from Earth, wouldn't they have to be from space to prevent elements in the Earth atmosphere from interfering? And that's a very good point.
So I think this person, yeah, got it bang on. I think that for like the SDSS things we were talking about before, that you can do from Earth because you're looking at a different part of the spectrum. So that's like looking at galaxy spectra, right? Which probably have their own problems, I'm sure. But for the most part, I think you can do it from Earth. Whereas looking at the planets, if you're looking at, like, I don't know, a water line in a planet, that will probably be hard because there's a lot of water in Earth's atmosphere. So I think they do need to be from space for the most part.
Yes,
Yeah.
yes.
Do you have anything to add?
I mean, also, actually, many of the recent European Space Agency satellite missions, or at least the proposed ones, are exoplanet ones. Like one of the most well-known one is the Kepler mission, which is basically a satellite that's made to search for exoplanets. Although I'm not sure if it's made to search for spectra, but many of the satellites have spectrographs to do exactly what you say. So to measure spectra from exoplanets without being influenced by Earth's atmosphere. Let's go to another question that we got on Reddit, which is how many black holes might be found in a galaxy? Does the galaxy size influence the number of black holes? It's maybe a bit connected to the question on YouTube of how do we detect black holes. Eric, do you want to, or should I?
I can give a quick go and then you can add in. So for the number of black holes in a galaxy, you would expect this to be correlated with the general size of the galaxy, the number of stars, because I would think that most black holes are going to be what we call stellar mass black holes that show up at the end of a star's life, specifically a massive star that dies faster than, right? So less massive stars live longer for stellar reasons. So if you have a high mass star, it'll die sooner and then potentially turn into a black hole. Now, exactly how many of those there are, I couldn't tell you.
Yeah, like I don't know the answer either. Like I don't know. I can probably Google it, but not sure. But basically, there are like, what is it, 100 million stars in the
What was
Milky
the
Way?
other question?
Sorry.
Oh no.
So that basically like 100 million stars in the Milky Way. And I'm not sure how many of, like, kind of, apart, like some stars after they die form black holes, and only stars that are more than, I think, 1 point a bit solar masses, like 1.5 or something. So only a fraction of those stars will form black holes. But basically all of those will form black holes as soon as they die. And since massive stars die usually faster than normal stars, I guess many of them will already have died. But I think we are not able to easily observe black holes that are just flying around without a companion or something. So I think it's very hard to do experimentally. And I'm not aware of any number that has been calculated. But I think you should be able to calculate it kind of from the number of stars we see and therefore from the number of dead massive stars we would expect. And yeah, how do we detect them? So as I just said, normal small black holes we can't really detect because they're just black and don't shine in any meaningful way. Massive black holes we can easily detect when they're like quasars, shining brightly, or with a black hole in our own Milky Way is what we did. Watch the stars that go by the black hole and see them kind of, when there's a black hole and a star goes past the black hole, it will make a very strong movement, like a very sharp change of direction, because a black hole is a really strong, it has a really strong gravitational pull. So that's actually really nice. You can look at time lapses of the galactic center and you see all the stars making really sharp turns about 1 point. And then we know that there must be the black hole. And actually, very recently, we were able to take a picture of an actual black hole. So what we did is, well, not we, what astronomers did is combine lots of radio telescopes all around Earth and combine them all to form a really high resolution image. And this is what they measured in the center of the galaxy M87, where we thought there was a black hole. We just got connection problems, but we're back. And in the center, what you see is kind of the shadow of the black hole. So that's the actual kind of size of the black hole in the center of that galaxy. So that's kind of the newest way of measuring black holes. but it's not really practical for anything that's too far away, because it's just too small, and the Earth, like even using all the telescopes on all of the Earth, that's kind of the highest resolution that you can achieve. So if the black hole would be 10 times further away than this, I don't think you could measure it. Another follow-up, even if not from space, it is possible for remnants of a star, say, present along the... So the question is if other things, for example, remnants of stars, interfere with the spectra that we measure from exoplanets that we discussed a few minutes ago. And basically, yes, like elements that are kind of around in the so-called interstellar medium would affect our, I think they would affect our absorption science, do they? I think, for example, the hydrogen line, I think you can observe in spectra. But basically, in the interstellar medium, all you will find is hydrogen, helium, and maybe a tiny bit of elements, but you won't find, say, oxygen, or well, like, I don't know, oxygen 2, or even ozone or something like this. That won't exist kind of out in space, or in only completely negligible quantities. So basically, you can look for certain elements that you would only find in the atmosphere of a planet, and those you could measure. You could measure from space and be sure that they come from the planet. Eric, are you still there, or is the internet connection broken?
Can you hear me?
I can hear you, but you're frozen.
Oh, well, yeah, I don't know what to do about that.
Oh, it's not too bad. We see you. Okay.
Yeah, look at that wonderful freeze frame of me, and it's good.
Could have been worse.
It could have been worse.
Okay, next question was, how do we measure the luminosity of a star? Oh, that's actually a good question, because what we can easily measure is what we call the apparent luminosity. So we look at a star and see, well, how bright is the spot on our telescope? You can measure this number, basically. But then, how bright is a star actually is a difficult question, because the further a star is away, or grammar is hard. Stars that are further away will look dimmer, even if they are, say, brighter or the same brightness than the star that is close to us. So what you have to correct for is kind of how far the star is away. And there are various ways of measuring how far objects are away. I won't go through all the details now. But basically, what you would do is measure how far the star is away, then correct for that and calculate like how bright it looks and how bright it actually is, given how bright it seems to be. So that's something.
So in cosmology, we're often interested in measuring distances, and so you look for something called a standard candle. So it'd be something that you believe is always the same luminosity or brightness or intrinsic luminosity, or at least something that you can standardize, maybe a standardizable standard candle, something that you can calibrate to be the same luminosity. And that the main one people use is a certain type of supernova called supernova 1A.
And that has always more or less the same brightness, or we can calculate how bright it is.
Yeah, it's calibratable.
And I guess then you can just invert the procedure that we just discussed. Like, instead of measuring the luminosity, you can use the observed luminosity to calculate how far the object is away. Oh, and I think we just lost you for a second. Ah, you're back. Your image is back. Nice. Okay. Since hydrogen and helium are present in relatively large quantities, like the CBM, what's CBM again? Anyway, if we simply point the spectroscope in space, will we see hydrogen and helium line everywhere? Oh, this is a very good question, and it's exactly what we're trying to do these days. So, yeah, right into my topic. My topic is what we call 21 centimeter cosmology, and the name 21 centimeter refers to exactly the hydrogen line. So we want to go in the universe and measure the hydrogen line all over the place. So this is already done since ages, basically, by radio astronomers within our Milky Way, and it's used to map out, the size of the Milky Way and the spiral arms, etc. So basically, you just point your telescope in space and measure all the hydrogen. The problem with hydrogen further away is very diluted. So outside of galaxies, there's very little hydrogen. So what you need is very, very accurate telescopes. And basically, you need radio telescopes, which means you need to build them on the ground on Earth. We want to build some on the moon, but we're not there yet. And and then you need to make very accurate measurements of kind of the hydrogen all over the cosmos. And it's very difficult because there are a lot of backgrounds. So for example, our own galaxies and other galaxies will emit also radio radiation. And that radiation is much, much stronger than the kind of hydrogen line that comes from extragalactic sources, especially from really high redshift, which means really far away. So there is actually, since, I'm not sure if it's already a year ago, probably, like from a bit more or so than a year, or maybe 2 years ago, there is a claimed detection of hydrogen from the very quite early universe. So exactly what you say, look into the hydrogen that's just flying around in space. But we're not yet sure if we actually, like, if that's actually a discovery or if they discovered measured something else. But it's a very active topic of research, and we're currently just in the era of our telescopes becoming good enough that we can measure the hydrogen in space, and we want to use that, to map out large part of the universe as soon as we can do that. So that's a very, very good question. Okay, let's maybe take one more of the Reddit question. What cosmological discovery is yet to be made that could potentially change the way we think of the universe? I mean, it's always very hard to predict future discoveries. Just that's the point of the discovery, right? So, I mean, one of the kind of nice candidates is what is it? A curvature of the universe. Like, I think most cosmologists, or at least people in astronomy, would think that the universe is flat. Or, I mean, at least I would think that's very likely. And if we would actually measure for certain that it's curved, I think that would be a big surprise to many people. Although it wouldn't be completely unheard of, because we already, we have the math, we have the equations for a curved universe. Maybe something like wormholes potentially would be a very exciting discovery that would certainly think the way many of us think about the universe. But we also have the mathematical framework for it already, because the mathematicians have been tirelessly working on coming up with interesting things. Dark matter would be also one.
I think something maybe like primordial non-Gaussianity, which, to say it briefly, is some signature you can observe that would tell you that there's something extra going on in the early universe. So that might be some extra addition to your theory of particle physics, for example.
Yeah. There's kind of the discoveries that are kind of on the schedule, right? I mean, there can always be something unexpected, but by the definition, we don't have no idea what it would be. Otherwise, we would be expecting it.
Should we segue into this periscope question?
Oh yeah, go ahead. What
So
evidence would be needed for a breakthrough in modern cosmology to occur?
Could be lots of things. I feel like the most straightforward answer I can think of off the top of my head would be if you have a detection of one of these things that people have been looking for a while now. For example, primordial gravitational waves, which I will interchangeably talk about as B modes, which, to say it briefly, is a particular signature that you look for in the cosmic microwave background. So it's in particular in the polarization. So
okay, let me give a bit more context before you go on with this. So a gravitational wave is basically a wave that travels to space that stretches and squashes space-time. Like, it makes really weird things happen. And we know those can be created, for example, from black holes merging, but they might also be created very early in the universe from kind of the inflationary phase of the universe. And this is what we would be able to observe, kind of like the effects of those waves in the early universe we could observe in the cosmic microwave background. And that's what Eric is talking about. Go ahead.
Perfect. Thank you. I mean, that was basically it, right? So if you get to a point where you can definitively get a signature of that, then that would tell you a lot about this inflationary epoch. People sometimes talk about B modes as being the smoking gun for inflation. And that'd be very interesting.
Yeah. Maybe another thing might be, there's currently this kind of discovery that I just mentioned of the 21 centimeter line. And one of the reasons why it's so disputed is that it doesn't look at all the way we expect, which is very exciting. And if that comes out to be true, so if it gets confirmed by other experiments, and we can exclude that it is an effect of the foregrounds or of the galaxy that we observe, then I think this would be a major change in how we think about how the universe worked in kind of around redshift 20-ish. And I think that would be also very, very interesting.
The other thing, of course, is if you have I don't know if confirmation is possible, but if we really start to believe that these tensions are real, and by tension I mean disagreements that we see in measurements of the same cosmological parameters, most famously the Hubble parameter, which is the expansion rate of the universe, between different measurements. So you end up with different answers. If we become very certain that this is not a measurement problem and is in fact a real physical thing, then that would be exciting. But as of yet, people haven't come up with a satisfactory theoretical solution, a satisfactory physical explanation that could be causing that, really. So I don't know if it's a breakthrough as such, but it's interesting.
Yeah. Okay, let's get back to some of the YouTube questions. We got a question, what is neutrino astronomy? I mean, the not so nice answer would be doing astronomy using neutrinos. Here comes a better answer. We can... Oh, now let me open the slide. So neutrinos, I should also explain this, why not? Neutrinos are a particle in the stellar model. So it's a particle we know, we have measured, we know it exists. And the special thing about neutrinos is they interact very rarely. So they basically fly through the universe and don't do much. I think actually through your body there will be thousands of neutrinos flying over a certain time. I think it's a few per minute. I think it's 1 per minute or something. Oh no, I think that was
surely it must be more.
More neutrinos. Anyway, lots of neutrinos flying through your body, and probably none of them are interacting within the next year or so. So they're really rarely interacting. But the nice thing is that also means they can fly through most things that we cannot look through. So if you could use neutrinos to observe the universe, you could find out lots of interesting things. And what we can do is build big detectors. So because neutrinos are so hard to measure, the simplest way to get around this is just take a huge detector. So what you see on the left is a kind of image of ice cube. So what they do is they go to Antarctica, take a few square kilometers of ice, and put detectors all in the ice. Or the alternative way is on the right hand side you see Super Kamiokande, which is a huge tank of water. I think it's water, is it? I think it's some special water, I'm not sure. Where they put detectors all over the edge, like you see them on the wall. Those are all photodetectors. And basically what you wait for is for a photon to fly through this water, and a neutrino fly through this water and interact, convert to something else. And then you see the end results of this interaction and can calculate where did the neutrino come from, what type of neutrino was it, and how did it fly, and can then use this to do astronomy. The problem is a bit that you get very few of those events. I think you discover only a few per day or so. I'm not sure about the details, but you can't really use this to, observe a galaxy. Actually, most of those neutrinos will come from the sun, and only very few come from other galaxies. I think there was at least one neutrino event where we think it came from a quasar, so from a different galaxy, and because it was basically the direction was matching pretty well, and it was also correlated with an outburst of this quasar that we observed with other telescope. So it's kind of starting the neutrino cosmology, but because astronomy, but because we need such huge areas, it's really hard. We still don't have a really good way to build detectors for neutrinos because they just don't want to interact with anything. You just need to build huge volume of something, and currently it's not. It's still a very exciting field, but it's not that you could make an image with neutrinos yet. Maybe it will be possible in the future. Okay, maybe one last question from Reddit. Can we know if our universe is embedded in a space with more than 3 dimensions? Is it possible that any of those are temporal rather than spatial? And yeah, it's also a question that I noticed that I'm not sure if we can answer in that much detail. So let me bring up the one thing. So basically, when we think about the, say, curvature of the universe, imagine first a 2D universe. Imagine our universe to be two-dimensional, be kind of just a plane, and it could be curved in a way that this plane is formed into a sphere. And then you would imagine, oh, this two-dimensional sphere in a three-dimensional space. But actually, you don't need to be embedded into a higher dimensional space to have a curvature. You could have a two-dimensional curved surface without necessarily being in a three-dimensional space. And the same is true for our three-dimensional universe. It could be curved, but it doesn't have to be embedded in a, say, four-dimensional space for it to be curved. So it's not necessarily, like, even if we would detect curvature, it wouldn't imply that there's another dimension. However, there are more exotic theories, like string theory and various variations, that predict many more dimensions than there are currently. Although I think all kind of space dimensions, I'm not sure about what an additional time dimension would be at all. But in some of those theories, I think you could, in theory, I'm saying theory a lot, detect interactions between those dimensions. So there could be some effects that you can only produce if there are like interactions with those different dimensions, and that would be a way to kind of know of those additional dimensions. But it's kind of a very niche theory. Like in the standard theory, there's only the 3 dimensions plus 1, so we wouldn't find any. But yeah, there are, like, of course, there are theories where there are more dimensions that we can never detect, but there are also theories where there are more dimensions and we could detect them. I think maybe like using the cosmic microwave background in very much detail, or some other observations. I'm not sure at all what would be required, or if it's in any way possible any time soon. But yeah,
we're way out of my wheelhouse now. So
yeah, I mean, out of mine too. Like I have never worked on these theories, so don't take my word for much at this point. Let's go back to the YouTube chat. We got a question: what is dark energy? Eric, do you want to explain this?
I'll take that one. So if we take first the observational thing, so if you the reason that we have a thing called dark energy basically is you look out into the universe and you measure all these galaxies and you say, oh wow, they're all moving away from us. That's weird. So this is how we come up with the idea that the universe is expanding, right? You measure, in effect, the velocities of all these faraway galaxies, and you see that they're all moving away from you. And unless you think that you're the center of the universe, which you shouldn't, this means that it's expanding, right? And then you look, and you can see that this expansion is actually, surprisingly, accelerating. So, oh, you have a slide for that?
I don't think so. I'll check if I have one. I have this one.
I can't see what's going on there. But anyway, yeah, that means that things that are farther away are going away from us faster. And as time goes on, we think that this expansion will get faster and faster. And this is contrary to what you would expect, because you think gravity, as Stefan was explaining before, should slow down this expansion and make things want to come closer together, as you usually expect gravity to do, right? So you need some explanation for why the expansion is accelerating, what's pushing all of these galaxies apart, and that explanation is dark energy. So that's one way. Well, I mean, that's basically the name that you give to whatever is making the things expand. So now, what is it exactly? That is, I would argue, still an open question. The standard model, the standard cosmological model, is what we call lambda CDM. The lambda stands for the cosmological constant. That is one option for what dark energy could be, and everything so far is consistent with that. We don't necessarily know that's the case. And if I say one more quick word about it, you can view the cosmological constant then as either just a term that you throw into general relativity that adds into the math, and this is how gravity works, Or another way to see it, which is just as valid, is as a vacuum energy density. So just some energy density that exists at all points in space. Yeah.
And that doesn't dilute when you expand space, which is really strange. Okay, one last question because we're almost over time. After the recent discovery of phosphine in Venus' atmosphere, how likely is it to find life, or how likely are we to find this?
I assume that means on Venus, no?
I guess in general, I think we can answer the question. So I mean, first maybe a small disclaimer: there is some controversy about the discovery of phosphine on Venus. So they're not sure if it's actually that real. But yeah, I didn't follow the news that detailed. But I think they just detected phosphine, and then there's a question: is this phosphine created by life, or is it created by some interesting chemistry? Well, of course, if it's created by life, then well, we probably found life, and if not, well, then we didn't find life on Venus. But basically, what we have to do is get more missions and make it more detailed look, and possibly send a spacecraft to Venus to look at this in detail. Basically, yeah, the part that we would see on Venus would be if you can kind of from like so-called abiotic, not organic, like boring molecules form kind of living cells. You wouldn't, we will not find a civilization on Venus. We would maybe find, like, if the phosphine is made by kind of living organisms, we might find, a cell or something like a bacteria. I don't know, maybe a bacterium or so. I'm not an expert on astrobiology, so don't quote me on the details. But we wouldn't find a civilization. We would find some really primitive cell-ish life form. With a big if, and in that case, if we would do so, then we would know, oh, it is possible. Like, Earth is not the only example of, forming life. And we would, like, our estimates for how hard is it to form life out of rocks and stuff would go kind of way up. And you would think it's much more likely to find life than otherwhere as well. So that's kind of the big effect. Yeah, I can't give you a number for this. Like, I have no idea. I think there are people trying to calculate numbers, but basically because we don't know a lot about most things that are about the formation of life, we don't really have very solid numbers about this. Yeah, and that's also past 7 p.m. UTC. So thank you all for watching. Thank you, Eric, for being here and answering all the questions. And
yeah, thank you, Stefan, and thanks everyone for your questions. They were great.
They were really great questions today. Yeah, thank you. Looking forward to seeing you probably next week. Follow us on Twitter to get the updates, but I'll try to be back in 7 days. Have a nice evening.